different. It's actually interact with magnetic fields. So neutrons do interact electromagnetically. Free Higgs particles, who knows? I don't know enough about Higgs particles to say much about them. There's lots of theories that would say they may interact via the weak force, actually. So there's a lot of good reasons to expect that WIMPs, in fact, their name suggests that they interact weakly. All right. So probably they do interact via the weak force. A lot of the dark matter candidates we have would interact via the weak force. So there's good reasons to suspect that, in fact, they would interact via the weak force. Right. So as I said, today we know machos can't be most of the dark matter. We need exotic particles of some sort. Well, how do we know this? Well, partly because we've ruled out machos because we looked for them. Well, what about gas we have? Can it just be very thin, tenuous gas? And the answer to that is no. And how do we know that? Well, I'm going to have to talk about the history of the whole universe. The universe starts with a bang, right here. We don't understand that at all, but we understand most of the stuff from here on out pretty well. Lots of things happen. There's dark ages, stars form, the sun forms, and finally there's you, right here. I want to ignore most of this. What I want to focus on is about 10 to 20 minutes after the Big Bang when the elements form. So the universe is a big soup of protons and neutrons and electrons and photons at this stage. Okay, it's a big soup of all that, all interacting with each other, and the elements form, and we understand that nuclear physics very well, that we can predict the ratios of the different elements. So what this plot on the horizontal axis is, the ratios of various different elements to hydrogen. So helium, helium-3, lithium, deuterium, that's what these four lines are. What is their relative abundance compared to hydrogen, which is most of the universe, all right, as a function of the baryonic density, all right? Baryonic, meaning the density of protons and neutrons. This green line tells you how many baryons we would need to get the mass to hold all the galaxy clusters together. This here, this gray thing, tells you the observed densities of these various elements all fall here. So helium is observed to have this density. Deuterium is observed to have that density. Helium-3 is observed to have that density. Lithium is observed to have that density. So that tells us, or that fraction, I'm sorry, I was saying densities, what I really meant was fractions. So the fractions of the elements all line up for this density, which tells us if we really believe we understand nuclear physics, which we do believe because we have used it to blow a lot of stuff up, as well as to do other kinds of nuclear physics experiments that are less destructive in cyclotrons and things. We understand nuclear physics well enough that the density of the early universe in baryons has to be a lot lower than the total mass we need to hold everything together. So where does this leave us? Galaxies are rotating too fast to be held together by the massive stars and gas that we see. Galaxies and clusters are flying too fast for the cluster to be held together by the massive stars and gas that we see. Measurements of the ratios of light elements tells us that there are not enough protons and neutrons in the universe to make up the extra mass. So even if it was just stars or gas or something that we haven't seen, that can't be the dark matter because protons and neutrons can't make up enough mass. So therefore, there must be some unseen dark is unseen matter, which is made of something other than normal protons and neutrons, also other than noble protons and neutrons. Noble protons and neutrons are protons and neutrons that are in neon or one of those. Normal protons and neutrons. Actually, protons, that's kind of a stupid thing to say because protons and neutrons are normal. So it's other than normal matter. Okay? Well, all right. Now, here's somebody who was asking this question earlier. Is it possible we don't understand gravity right? Well, yes, that's entirely possible. Somebody was asking almost specifically the question, could it just be that in the far parts of galaxies, gravity works differently from how we thought it did? So, can we get by without dark matter? And this was Milgram proposed in 1983, a specific model, which here it is. A modification of the Newtonian dynamics is a possible alternative to the hidden mass hypothesis. And the basic idea is, well, okay, Newtonian gravity is well tested in the lab. It's extremely well tested in the solar system. But galaxies are big extrapolations in scale from these regimes, in that the gravitational force on stars very distant from the center of the galaxy turns out to be really low. And they take forever to go around. Right, and so is it right, and what Bao says really hits the nail on the head. He's not sure that, or she, sorry, is not sure that it's more parsimonious than the dark matter, but it feels like it is. A lot of people felt that way. A lot of people feel like dark matter is more parsimonious than modifying gravity we understood. So it's almost sort of a philosophical or an aesthetic argument, which is more parsimonious. But, well, we got to think about it, all right? And here's the basic idea. Maybe galaxy is just different on the scale of galaxies, and we can explain galaxy rotation curves without needing to invoke dark matter. Here's another choice quote on this. This is a review from 2002 by Sanders and McGaw about MOND, or modified Newtonian dynamics, which is basically Milgram's idea. And I'm going to just go ahead and read this quote. It may be argued that MOND is a speculative topic for a review in this series. Right? ARAA is a very serious astronomy journal, so, how could we talk about MOND? In our opinion, the subject of dark matter, and Virginia Trimble is cited here, is, in the absence of its direct detection, no less speculative, particularly concerning that the standard model of particle physics does not predict the existence of candidate dark matter particles with the necessary properties. And this review and other reviews that have been done went on to conclude that, well, given the evidence we had on galaxy rotation curves, it was really hard to distinguish between dark matter and saying we just didn't understand gravity. What we really needed in order to prove that dark matter is there is sort of direct detection, which means seeing matter where we don't see baryonic matter. Well, okay, we've done that. But to understand what we've done that, I have to take a slight sideline and talk about galaxy clusters, which I've already been talking about. But here's your list of facts about galaxy clusters. So when you're playing Trivial Pursuit and somebody says, what percent of the mass of a galaxy cluster, of the baryonic mass of a galaxy cluster is stellar, you can answer, right, and get a little wedge in your little thing. So galaxy clusters are hundreds to thousands of galaxies, all clustered together in something that's something like 3 to 30 million light years in diameter, which is small on the scale of the universe, is big on the scale of a bread box. 10 to 15% of the baryonic mass, meaning the protons and neutrons, is in stars. Most of the baryonic mass, it turns out, is in very hot million-degree gas that's spread throughout the cluster. Right? This is part of Zwicky's dark matter, in fact. Zwicky said, hey, I need more mass than I can see in these galaxies. Well, here's some of it. Turns out it's not enough, but some of it is the X-ray emitting intracluster plasma. We call it X-ray emitting because that's how we see it, right? What really is important is that it's plasma and it's at millions of degrees, all right? And because of that, and why doesn't, that's an excellent question. It will, but the time it's going to take to cool down is longer than the age of the universe. So it's radiating some of that energy. The X-rays we see is that energy radiating. The reason it doesn't radiate faster is because it's so low density. So one of the dominant ways for the energy to radiate is for an electron to pass a proton or another electron and curve and radiate a little bit of its energy and slow down. For example, that's called free radiation in astronomy jargon, and that's happening. But because the density is low enough, it doesn't happen often enough for the energy to efficiently radiate away all that fast. So it's going to take billions of years. It's not, and Drew says it's not quite blackbody radiation. It has a different spectrum from blackbody radiation. It's not pure thermal. We do talk about thermal free radiation, but it's not quite the same thing. All right, so it's plasma radiation, and we see it in X-rays because that's where a lot of it is. So the baryonic mass is an X-ray. That's where most of the protons and neutrons, it turns out, right? These galaxies are kind of along for the ride, right? But again, if we use standard Newtonian gravity, not MOND, the gas accounts for something like 5 to 15% of the total mass of the cluster. In other words, most of it still has to be dark matter. Well, okay, let's talk about merging galaxy clusters. Galaxies are mostly collisionless, that is, they pass past each other. Some galaxies do run into each other, but by and large, if you take two galaxy clusters and run them into each other, it's like taking two handfuls of sand and throwing them past each other. Occasionally, 2 grains of sand will run into each other. Mostly the sand just goes past each other. The intracluster gas, however, is a big blob, and it does interact via fluid stuff, fluid dynamics, viscosity. Well, actually, it's plasma fluid dynamics. So there's all kinds of stuff that goes on. But that's like taking 2 handfuls of water and trying to splash it into each other. If you take 2 cupfuls of water and you manage to throw it at each other, it splashes in the middle and kind of all stops there and splashes around and makes a big mess. So the galaxy clusters are collisionless, throwing 2 handfuls of sand at each other. Mostly they pass past each other. The intracluster stuff is more fluidy, and it's like throwing 2 blobs of water at each other. If there is non-baryonic weakly interacting dark matter, it will also be collisionless. Because it's weakly interacting, mostly particles don't run into each other. Yeah, dark matter exhibits momentum because it has mass, and anytime you have mass and you move it, it has momentum. So it'll have kinetic energy as well as mass energy. All right, so non-baryonic, weakly interacting dark matter will also be collisionless. Well, all right, but how can we figure out where there is mass that we can't see? Well, from its gravity, but what we want is to have another way to do it. Well, it turns out it's still from the gravity, and that is, there's this thing called gravitational lensing. If you look at a star, here's a distant star, and there's a star in between you and it, it turns out that the gravity of this star will bend the light rays coming from this star. Right? So in this case, this is strong lensing that we're talking about here. In this case, the light ray that was going in this direction gets bent by the gravity of this star and comes at you in this direction. So that what you see is light coming from this direction, which makes you think you'd actually see a star out here. Similarly for down here. So this is a case here, this is Einstein's cross. The thing in the middle is the lensing object, this, and the four stars on the outside, this is actually quasars, but the principle is the same. These are quasars that you see multiple images of as a result of the bending of light here. They're all the same quasar, but you see multiple images because the light rays were bent here. So gravity can bend light. Here's a classic example, the cluster Abell 2218, and because of the expansion of the universe, the image has now started to cover the letters. But there are two galaxy clusters here, actually. All the yellow things are foreground galaxies, and then these streaks you see are background galaxies from a background cluster whose light has been streaked and distorted by the galaxy of the Fluss. And yes, Reynolds numbers are used when calculating. I mean, there's all kind. I'm not an expert on plasma fluid dynamics, so I can't really tell you. I mean, Reynolds numbers probably go into it, but I don't know the details. What is there a star in those other two places, the light from both? How can you distinguish the two? Well, all right, so there's ways we can distinguish. But if you measure the redshifts here, you'll see that there's two different redshifts. So the yellow galaxies are all at one redshift. I don't remember what it is. The other streaks are all at a much higher redshift. And in fact, there's other galaxies mixed in as well, but mostly that's what you're seeing here. So that's one way to distinguish is by the redshift. And we see all the high redshift ones are stretched out. So what this tells us is that we can see where the mass is by looking how galaxies get stretched out and distorted. Now what we really do is this thing called weak lensing, which is where it's not big, huge effects like I showed you before, but if I am looking at a galaxy here, and it's going between mass, there's all the mass in the universe between it and me, the galaxy's rays are going to be a little bit distorted, only at the few percent level. So if we look at a whole bunch of galaxies, background galaxies, in a field of view, we can see them all distorted at a few percent level, and we can figure out how much mass the light has gone by in order to distort them all. This is very hard to do. In order to measure the distortions at the few percent level is a very difficult problem. But, scientists do difficult things, and eventually they figure out how to do it. And so now we have this thing called the bullet cluster. Now, all right, this is another complicated image. So what I'm going to do is, first of all, point out, you notice here there's a collection of galaxies, and there's a collection of galaxies. What they are two clusters of galaxies that have actually passed through each other. How do we know they've passed through each other? Well, the pink is X-ray observations of the intracluster gas, this hot X-ray emitting gas, and you'll notice that it's all kind of clumped in between the two clusters of galaxies. Here's the bigger cluster, here's the smaller cluster. As they passed through each other, the gas got stripped out, and in fact you can even see this gas here sort of in a little bow-shock formation as a result of all the fluid interactions. You could do simple fluid modeling to show that, yeah, it really works like this. So you have here all the galaxies which just passed each other. They're like the handfuls of sand, and collected in the middle you have all the fluid, you have all of the intracluster gas stripped out and stuck in the middle. But then what blue is, the blue haze, is where is most of the mass of this cluster. Now most of the baryonic mass is here, because we know that most of the baryonic mass is in this X-ray emitting gas. So most